All right, guys, welcome to Intro to Counting and Probability class 13. Today we're going to talk about the hockey stick identity. It's, like we've already talked about certain combinatorial identities, right? You guys, I'm sure, had a lot of fun with last week's homework, proving things. But today we're not going to prove anything. I'll still be proving it. But we'll be talking about the hockey stick identity, which is a very interesting identity that also introduces us to a concept called stars and bars, which we will go over today. It's pretty useful, and that's really about it. There's nothing else I should need to say. It's one identity, but it can be used in a few different ways. So this is why we're doing a whole chapter on it. Cool. Cool. Okay, so let's just get started then. So today we're going to talk about the hockey stick identity. So I'm going to provide some background first because I think that's always important to do. So let's consider the following question, okay? I have 12 indistinguishable pieces of candy. Right? We all remember what indistinguishable means. It means there's no difference between two. Indistinguishable candies and 4 distinguishable kids, okay? All right, so that's the premise of the guide, and we're trying to distribute candies. We're trying to distribute candies to kids. So our question is, how many ways can we distribute all 12 candies? You can't not distribute. All 12 candies have to go to one kid. All 12 candies to the 4 kids, right? And so note that kids can get 0 candies. So it's not like everyone needs a candy. You know what I mean? Awfully cruel. You could give all the candies to one. You did not change your name. I did not change your name for you. I mean, I can do that, but I didn't change your name. So but that's not what it is. So the question is, how many ways can you do it? Well, and Aaron, it's not 12 choose 4 because that would be just choosing 4 candies to distribute to the kids. So that'd be choosing 4 candies out of the 12. But you're not choosing 4 candies here. You're choosing to distribute 12 candies amongst 4 kids. Now, okay, well, let me ask this question first. If it was if these candies were distinguishable, what would the answer have been? Does anyone know? If the candies were distinguishable, does anyone know what the answer to this question would be? Well, you don't have to give me the actual answer. You can just give me like the unsimplified version if you don't know what that number is, because I don't. It's a pretty big number. Right, so this would be the distinguishable case. And do you remember how we do this double distinguishable case? Well, think about what choices you have. Because this one's like a choice. It's like a matter of choice. It's just like side questions. I don't think too hard about it. 12 to the 4. Wait. Okay, wait. I'm waiting. I'm waiting. Nancy, you may choose to give me that answer or choose a different answer. It's up to you. Anyone else have any answers? Yes, Howard, we will be talking about that today. I know what you're talking about. We will be talking about that today. But we need to go through, but it's mostly about the hockey stick identity, so we need to go through that first today. Well, it turned out to be 4 to the 12, right? Because for every one of the 12 candies, there are 4 different kids you can go to, right? You can either go to kid 1, kid 2, kid 3, or kid 4, and you need to do this for every single candy. So it's 4 to the 12. Now, of course, very importantly, if the candies are indistinguishable, you cannot do this because in such a case, giving a candies A and B are the same as giving a candy C and D. It doesn't matter as long as they get 2. Cool, right? We all understand why it's 4 to the 12, right? Yeah, awesome. Okay, we still remember that stuff. So Now, unfortunately, this question is not easy to do with our current knowledge, okay? And you'll remember when we talked about distinguishability back in the day, we kind of just listed them last time, right? We had like four, like, I don't know, 2 boxes and 4 balls or something. We kind of listed them out. So today we're going to talk about ways that we can avoid listing them out, because back in the day, yes, that was like 5 weeks ago. That's really old back in the day. So okay, we see what we have here, right? And we want to think about how we can do this. Now this is not apparent how we do this, but what we could consider is simplifying, is think of like a lesser problem, right? And we could, like, we could get rid of we could like lower the number of candies. We could lower the number of kids. For our sake, we will be lowering the number of kids, and you will see why momentarily, okay? So let's consider a really easy example, okay? 12 candies, 0 kids. If we had 12 candies and 0 kids, how many ways are there to do it? 1, correct. Okay, let's just move on. How about if you had 1 kid? No, 1, I guess, correct. Again, you can only give all your candies to 1 kid. Okay, cool. Again, not too exciting. 2 kids. You can't give them to yourself. 144, that is not exactly it. Or if there are 2 kids. No, again, remember, this is not distinguishable. We're not talking about these are not distinguishable anymore. We're still working on our indistinguishable candies. That was just like a side note, just to refresh you guys. You do have to list it out, but is there a smarter way you can, like if you just, okay, list out, give me an example of a distribution of candies I can give among kids. What is one way I could do 12? 0, 0, 12, okay. 12, 0, cool. 6, 6, yeah, that they all work. 11, 1, 10, 2, exactly. So hopefully at this point, you don't actually have to list them out. You can actually, hopefully everyone sees why the answer is 13, right? Because you can go from 0 to 12, and you can like add 1 and subtract 1 over and over again to get all of the 12, 0, and there's 13 different pairs here, right? So hopefully that wasn't too crazy for anyone. Cool. And in fact, you know what? I'm gonna say this n candies. You'll see why I say n candies. Okay. So this will become n plus 1, obviously. Right. And n plus 1. Yeah. Become n plus 1. Right. Are we good? Does that make sense, people? I'll change this to n. So we're just doing. I've decided halfway through we're doing n. We're doing n candies. Cool. All right, awesome. So now let's consider until you have 3 kids, okay? Now it gets harder. Now, of course, it gets harder now. But, well, what do we notice? Let's suppose. Okay, so let's suppose we give some candies to the first kid, okay? So 3 kids. Let's say we give X candies, or no, how about X candies to the first kid, okay? We decide how many ways are there to distribute amongst the 2 kids, the other 2 kids. N minus x plus 1. Why is it n minus x plus 1, Howard? That's an interesting proposition. Where are you getting that from? Once you give the 1 kid X candies, yeah, you have X. You mean n minus x, but yes. Oh, n is the number of candies. I've decided we're going from 12 to n. We're generalizing. Where it's n plus 1, right? So what Howard is noting that at this point it's the same problem as above, because what you're doing now is you're doing n minus x candies and 2 kids, right? That's what Howard is saying. We reduced the 3 kids problem to a 2 kids problem by assigning 1 value to the x. Now the question here is, then this process. Oh, I'm glad you noticed, Charles. Now, unfortunately, this repetition isn't very helpful, so we still want like a concrete way to think about it. So how do we go about, what would the answer to this question be? Because sure, we consider for one x, but we still want to find it for all, like we don't care about just x. So how do we do this? Or how about this? How many cases do we have to consider? Right? Because we can indeed do this. This is completely right, and we can reduce it down to this problem. But what about, but we still need to solve the entire problem, right? There is also symmetry. You have a point, but that's not going to be super helpful for us right now. What I'm interested in is you decided that once you assigned one kid a certain amount of candies, the problem reduced down to a previous problem, right? But that doesn't help. That doesn't completely solve the entire question we care about of n candies, 3 kids, right? So my question is, what is the calculation we want to do, or how about it, or like, because this was for a very specific value of x. How can we generalize this so it counts everything that we need? Does anybody know? Well, what can we do? We know if we know what this about x is, we know how many there are. So what can we do about x? Subtract? Well, I mean, we are subtracting the n minus x. You're all right about that. But no, what I'm saying is this solves a specific subset of the problem, right? This solves the problem of n candies, 3 kids if the first person gets x. But obviously we can't have that restriction when we're solving the entire question, right? We can't possibly have that as a restriction when we're solving the entire problem. So my question is, add x to what is it exactly? I don't know. Okay. Well, what I was thinking, why don't we just case on x, right? Because what values can x take? Any. Well, specifically? Again, guys, we're not focusing just on 12 anymore. I want to make it clear that we are dealing with n candies exactly now. Yes, any number from 0 to n, right? So what we're doing here is we're saying if x is 0, then we have I'm going to use like curly brackets to represent like the sub problem, okay? And if x is 1, we have the n minus 1 case of problem, right? Again, this notation, this curly bracket notation I'm doing just represents the problem, like the n minus 1 candy 2 kids problem, right? It represents it's like a hypothetical value that was there for I don't have to rewrite everything, right? And this will continue all the way down to x equals n, to which it's 0, 2, right? So fair enough. So that means the answer to the question n3, right? The answer to the question n3, oh, why am I in snap mode? Get that out of my face. The answer to the question n3 is simply the sum from I equals 0 to n of the I2 version. Right? And if you don't know what that means, because you've never seen this before, that's fine. I'll write it out for you. If you've never seen sigma, don't worry. I'm not going to make you know sigma. Like that. Yes, you're adding, right? Because it's casework, right? We've done casework before, right? Everyone remembers what casework is, right? Oh, hopefully, no. Casework was a while ago, something, maybe. Cool. Does that make sense? Now, what's interesting about this question, and where does the hockey stick? You'll see these appears to have no hockey. We're really building up there. We're doing a whole class on it, so you probably won't see the hockey stick until like the second half. But you see this, right? Now in the 2 case, we know that the 2 case is just n plus 1, right? So we can actually just fill this in for ourselves. So we can say this is equal to n plus 1 plus n minus 1 plus plus 1, right? Now, do we recognize what this value is? Does anyone know what this simplifies to? This little expression here. Well, how do we add numbers from 1 to, well, remember we're doing n plus 1, right? We're not ending in n, we're ending in n plus 1 here. Right? So that does change the value a little bit. Who remembers? Correct. N plus 1 times n plus 2 over 2. And for our sake, we're going to write this as n plus 2 choose 2. Right? We all agree that's n plus 2 choose 2. Cool. So for n and 3, we have the answer of n plus 2 choose 2, which is, definitely something, right? Now, okay. This is cool and all. But, right, like, this doesn't really, this is not where we hit it with the hockey stick. No. Now, what's going to be interesting here is that, like, for example, if you did n and 4, right, let's say, well, then we would know that to be, according to our previous answer, it'd be the same thing with n and 3 and n minus 1 and 3, right? It'd be the same deal, except now we're dealing in the 3 case, right? Plus 0, 3, right? Does that make sense, right? It's the same concept as before if we have 4 kids. It's just now we're assigning the first value to the first kid again, and we're just dealing with the other n minus x candies with the other 3 kids, right? And we can also fill this in with what we know to be n choose 2. So we could be like, that's n plus 2 choose 3 plus n plus 1 choose 3. Oh, not choose 3, choose 2. My bad. I'm a liar. Choose 2 plus n choose 2 plus n minus 1 choose 2. And this would go all the way down to 2 choose 2. Right? Do we agree with that? And of course, we're not actually sure what this value is yet, so that's unfortunate. But what is interesting to note is, let's say we did this let's say we did this value out for a bunch of pieces and a bunch of kids, and let's say we had let's say I'll have a graph going, okay? So let's say this is number of candies and number of kids, okay? It's a kid. It's like a person, So I'm gonna present you this little graph, and I want people to see if they see anything. How low do I go? So 5. Yeah. So obviously with 0 candies, it's one way to do each of these, and with 1 kid, there's one way to do each of these, so it's not like a big problem. 2, 3, 4, 3, 6, 10, 4, 10, 20, 5, 15, 35, and 6, 21, 56. It's Pascal triangle, but rotated. It's Pascal's rectangle, I guess, right? Pascal's rectangle, right? Do we see Pascal's triangle or rectangle or whatever you want to call it, right? Do we see the rows of Pascal's triangle? We're gonna go with that, and there'd be a 1 here if we get 5. Pascal's shape. I'm glad people are coming with such innovative. Yes, but this is Pascal's triangle, and so we know. And so we know what each of these values are in terms of a combination, right? So it turns out that with n candies and k kids, the answer turned out to be n plus k minus 1 choose k minus 1. So that's kind of interesting, right? Now, unfortunately, that's not proof for the reason why. But hopefully you guys, is that hog? He's like, we're getting there. Do not worry. Does that make sense? Cool. If that makes sense, then we'll have a little intermission. How does a rectangle work? Well, it's just Pascal's triangle rotated. looks like a rectangle. But I mean, it like how it works is that it adds the one to the right and above it. It's like Pascal. It basically is that. Yeah, I just said Pascal's rectangle because it looks like a rectangle right now. Cool. Let's do some problems. We'll do an intermission for problems, just to see if you guys really understood what I was talking about. So just try out the 3 problems there. I'll give you guys 20 minutes. And when we come back, we'll talk about the reason as to why this is the solution, right? And then finally, we'll choose the hockey stick identity, and that will be basically it because there's nothing else to do in this here. So take 20 minutes to try these questions out. Let me know how far you get. And again, these aren't meant to be hard. Think about how remember what we did here? We considered a problem based on previous problems, right? We said this problem is equal to a problem, right? This problem is the same as this problem and this problem, this problem, this problem together. So try to think like that when you're doing the problems, and that might help you a little. The candies continue to be indistinguishable, yes. However, for 13.3.3, you'll notice that they talk about 2 types of candies. The 2 types they're indistinguishable, period. Although for problem 3, you'll notice that there are 5 pieces of cinnamon candy and 6 pieces of butterscotch candy. The 5 cinnamon candies are indistinguishable amongst themselves, and same with butterscotch. But obviously, a cinnamon candy is different from butterscotch candy. So for 13.3.3, it's like a mix, right? Where they're distinguishable based on the fact that they're a type of candy, but they're indistinguishable amongst themselves. All right. So try the questions out. Good luck. Think about what we did. I'll heal the formula for you here. It's n minus k. I think it's plus 1. No, I lied. It's n plus k minus 1. Choose k minus 1 for n candies, k kids. All right. Good luck. You can use the formula for one of them, but good luck using the formula for the other ones. That's not going to be you're not going to be laughing anymore, Howard. I'm going to be the one laughing. I'm going to laugh at the tears you weep, knowing that. Oh, someone has a choosing calculator. Well, lucky them. You don't have to simplify your answers if you don't want. You can leave it in choose notation. That's fine by me. Oh, you already cried. Okay, so you win. I guess Howard wins in this case. He did cry. He cried out all of his tears last week. I guess he's none to cry out now. From the combinatorial things, understandable. That was a really hard chapter, so I totally get if you guys struggled, because it's like proof and you guys never did proofs before, and so just throwing you into combinatorial proofs is probably not hard. It's probably hard. He outsmarted you outsmarting but in the dumbest way possible. So it's like he went a full circle. It's really well done, actually. You guys can go on break. So let's quickly go over what we did because I forgot to record again. 13.3.1 should be pretty obvious. It's just a direct application of the formula. So you apply the formula, you get the answer. For 13.3.2, the key idea here is that if every kid needs to get at least 1 candy, just give them all the 1 candy first, and then you're able to do 7 candies and 4 kids without any restriction, right? You'll be able to, because once you distribute 1 kid among them, you can assign an additional 0 candies to any kid, so it's not a restriction. So you have 7 plus 4 minus 1, choose 4 minus 1, which is 120. And finally, for 13.3.3, notice that a distribution of the cinnamon candies and a distribution of the butterscotch candies are independent, right? However you choose to distribute the cinnamon does not impact how you can distribute the butterscotch. So it's independent, so you can multiply the number of ways to distribute the cinnamon ones and by the number of ways to multiply by the butterscotch ones, which would give you the answer of 4,704. And those are the 3 problems we just did. So let me know you're back by typing in the chat or indicating in the Zoom thing, whatever, somehow. And you have returned. Hello, Nancy. Hello, Howard. I am re-recording. Do not worry. The recording is reading. Hello, Aaron. Anyone else present today? And would like to tell me that they are indeed here. Hello, Ling. Hello, Rocky. Hello, Charles. Oh, he's coming up with something funny. Okay, we'll give him a second then. And hello, Ryan. Okay, So it is now. You're still currently absent. Okay, awesome. So right now we're gonna talk about. So we know the formula, but unfortunately we still don't have a good reason why, apart from it looks like Pascal's triangle. So let's come up with the reason why. So let's think about it this way, okay? So imagine we lined up all 12 candies in a row, okay? I'm not gonna. I won't draw 12. Let's say we're doing this for 7 candies, okay? 7 candies and 4 kids, okay? Hello, Charles. So if we have 4 kids and 7 candies, right? How can we distribute these candies among these 4 kids? Well, what we could do is notice that we don't have to we're not gonna do I'm not gonna give this kid this candy. I'm gonna decide to give kids adjacent candies, okay? So I'm gonna give them like a group. So every kid gets a group of candies, right? So for example, I can assign the first kid this many candies. I can give the second kid this many candies. I can give the third kid no candies, and I can give the fourth kid the other 2 candies, right? So by making sure they're adjacent, I can still make every arrangement I care about. Does that make sense? Right? I don't have to like pick and choose. I can just like take 2 candies from the queue and take 3 candies from the queue. Okay. Now think about it this way. Okay. Now we can think about it as almost like in a conveyor belt, almost, right? Not a conveyor belt. Well, imagine like you're shopping, right? You're shopping and you're at the cash register, and there are these 4 kids in the line with their candies. Okay. Now how do that was a good voice check. How do we in a grocery store, how do we recognize, like, if the 4 kids are here, right, and they're like they've got their mom's credit card or something, I don't know how they're buying these candies from the grocery store. How do we indicate, how does the cash register know which one belongs to kid 1 and which one belongs to kid 2, which one belongs to kid 3? Does anyone know what they do in grocery stores? Come on, you guys have gone shopping before, right? Come on, someone tell me. They do you really think they do that at the cash register of a grocery store? Well, think about it this way: when you're loading things from the grocery store to the cash register, what is the first thing you do when you get there? When you're like waiting behind the kid, well, not like kid. When you're waiting behind the person, people like you've got other people with their stuff. You put the bar, correct? You put the bar, right? If someone else pulls up, some like adult, will indicate an adult by wearing a hat. He comes up with his like groceries. He puts the bar first. They got like a bunch of bars here, right? They put the bar first, and they put their like groceries. I don't know what they have, right? So a good way for us to indicate that these kids are candies is through dividers, right? For example, if we think about the example before, we can give this kid 2 candies, so we're gonna put a divider here, to let the cash register know that these 2 candies belong to the first kid. Then we can put the second kid can have 3 here, and now let's say for example, this kid didn't actually get anything, it's just trolling, so they put another divider, right, just to let him know that I'm not buying anything, I'm just here for the fun. Maybe he buys something else. Maybe he's got maybe he's healthy. Maybe he got an apple. I don't know. That's an apple, okay? Maybe he got an apple. But there's no candies here, right? So we can imagine, for our sake, that there's nothing there. And finally, the 4th kid doesn't actually need another one because there's no one behind him. Let's assume there's no one behind him. So he can so we only need 3 dividers, right? This is very critical. We only need 3 dividers for 4 kids. Or, yeah. Does that make sense? For 4 kids. Now if we forget the kids and forget the conveyor belt, forget the kids. Oh no. Let's just take a look at this again. We have 7 candies, now we have 3 dividers. Would you agree that if I arrange these 3 dividers and these 7 candies, they would represent, any arrangement that would represent a certain amount of a certain set arrangement, right? For example, if I put, I'm gonna draw like circles and things now. For example, what would this be? This is an extreme example, but this is still an example. What does this represent? this arrangement of candies and bars? Like, what is the distribution of candies here? Well, I'm not asking for the answer. I'm asking for like what distribution of candies does this represent? The green thing here. What does this represent? Like what one kid? Which kid? Which specifically which kid? There are 2 middle kids when there are 4 kids. The third kid, right? The third kid is getting all of them because this is the first kid's over here, the second kid's over here, so the third kid is over here, and the fourth kid's over there, right? The dividers divide up the kids' purchases or whatever. So if every single arrangement of these candies and bars, third kid really bought out the entire stock, what can you say? If you do this, then the question just becomes how many ways can I arrange seven candies in 3 dividers? And what is the answer to how many ways I can arrange those? 10 choose 7, right? Because you do 7 plus 3. Well, we'll do choose 3, and you'll see why. Now, I don't care what the exact answer is. That's not important to me. But now we extend this to n candies and k kids. But of course, instead of k kids, what are we really dealing with now? Now, instead of k kids, what are we dealing with? 120, thank you very much. Instead of k kids, what do we have? Right? What are we actually organizing? What are we actually ordering here? K dividers. Well, do we have k dividers? We have k minus 1 dividers, correct? Right? We think about the grocery line, and we realize that you only have to distribute between them. You don't actually have to like put 1 at the end of each one of them. So you actually have k minus 1 dividers. So we're ordering n candies and k minus 1 dividers, which means that we have n plus k minus 1 things, and we're choosing k minus 1 things, and that's where the formula comes from. Cool? Who is blown away by this fact? Manila blown away. Who understands this fact? Let's start simpler. Who understands? Do you guys understand why we are able to change the idea of distributing indistinguishable candies to a concept of putting in dividers between candies and organizing those? Cool. Who are people feeling good about this? If you're feeling good about this, right, then we can finally get to today's main topic, which is hockey stick theorem. Okay. By the way, this technique is called stars and bars. There are a bunch of other names, and I will happily take other names that you guys have for this. I think there was like in wines and lines, right? Although wines and lines has a different like connotation per se. Lines at least has a different connotation that I will not go over. Stars and bars, wines and lines. If it rhymes, it's fine. I don't know what else there is. I think there's something else. There are other like this and this. The point is, if you see something and something and they rhyme, it probably refers to this technique, where instead of distributing, you're using your bars. If you put in dividers and you organize those indistinguishable objects, then we call it a stars and bars, a wines and lines, or whatever you want. Cool? All right, hockey stick theorem. So we know what do we know? We know n plus k minus 1 choose k minus 1 is the answer to the n kids wrong way k kids and candies question, right? Now, remember what we said earlier today? We said if we choose to do x, put x here, right? For one kid, then the rest of the question is just distributing n minus x candies to k minus 1 kids, right? right? We remember that, right? This is something that we came up with because we realized, well, if we pick how many ways there are to take, if we decide how many the first kid gets, then the rest of the question is just distributing the rest of the candies to the rest of the kids. Cool. So with that in mind, what if you give one candy to one kid, but they don't like the flavor they give back to you? No, we shove it. We make sure they eat it. We will force choke it down their throat. That's the answer to your question, Howard. By the way, that is what happens actually in real life. So with that in mind, right, and we were discussing different cases, right? So we were like, we can do this for the n minus x, k minus 1 case, or sorry, the n case, right? The case of just n kids, but with x is 1, we can do it with n minus 1 kids, or we can do it with n minus 2 kids, or we can do it with n minus 3 kids, and you do this all the way down to 0 0 candies, right? We're gonna move this. Oopsie doopsie. Right, that makes sense. But of course, we know that this is equal to the case of n choose k, or n and k. So we can represent each of these as a binomial as well, right? Specifically, this part here becomes n plus k minus 2 choose k minus 2. This one becomes, and again, we're adding them together, right? I forgot to put addition signs here, right? But we are adding them together, right? Because it's it's a casework, you know, the different cases, whatever. And this one becomes n plus k minus 3 choose k minus 2. And this one is n plus k minus 4 choose k plus 2, k minus 2. And this goes all the way down to just k minus 2 choose k minus 2. Okay, does that make sense? Right, and again, that's just us plugging these cases of the question back into the formula we already know, right? Cool. So that's it. That is the entirety of the hockey stick theorem. Now in general, we like to substitute the well, you will see why it's called hockey stick theorem. Do not worry. So we tend to, instead of saying n plus k minus 1 and k minus 1, what we like to do instead is usually we write it like this. We have n choose r plus n minus 1 choose r plus all the way to r choose r, and we say it's n plus 1 choose r plus 1. This is how we usually write it. Now, of course, we write this way is the direct result of this is the direct result of our analysis of the candy kid question. But we just basically here what we do is we let r equals k, and we let n equals I think n plus k minus 2, basically, right? We're just reassigning some variables, and it's the same equation, but it's just, you know, it looks prettier like this. So why is it called the hockey stick theorem? Well, let's someone give me an n and someone give me like a small n and a small r, like reasonably, that I can draw it on Pascal's triangle, you know. So let's then consider example of n equals, who wants to give me an example? 1, well, no, that's too small of a hockey stick, I'm afraid. You're gonna have to pick different n's and r's, I'm afraid. 5, 3, I like that. Sure. Let's do n is 5, r is 3. Okay. So what this equation is saying is that 5 choose 3 plus 4 choose 3 plus 3 choose 3 is 6 choose 4, right? That's what this equation, which is true. You can check it. Now let's draw these values on Pascal's triangle. Okay. So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5. I need the second row as well. I need the last row. 1, 6, 15, 20, 15, 6, 1. Okay. So let's see where each of these values lie. Okay. So 5 choose 3 would be this value here. We agree. 4 choose 3, this value right here. And 3 choose 3, this value right here. And finally, we have 6 choose 4, which is over here. And behold, the hockey stick. And notice that as your difference between n and r increases, your hockey stick length also increases, right? For example, you can go all the way up to here and do this. And this is also a legitimate hockey stick because, right, again, you're adding You're adding all numbers from 1 to 5 and adds up to 15. And so hence this is called the hockey stick theorem. And so this is what we've been leading up to today. It's actually an identity, my bad. I've been lying to you, it's an identity. Hockey stick identity, it looks like a hockey stick. Now, of course, that means the hockey stick identity works the other way too, because you can do it this way, right? You can also do it, you can also make left facing hockey stick, right? Because it's symmetric, right? Due to symmetry. Like this mahogany one I drew is the symmetric of the pink one, for example, right? So symmetry still applies in our case. But you can transfer any single way. You basically start at a 1. What this cool question is, you start at any one of the ones you want, and you go down in the direction that matters, up to a certain point, you add it all up, and then you move to the right one or the other direction, and the sum works. That's what this tells us. Cool? Who thinks this is actually legitimately cool? Because this might be the coolest thing combinatorics has done for us today. Well, if n is less than r, then I don't think this formula means anything to us, Howard. So maybe we won't consider that. Technically, it's still true, because that would mean 0 is equal to 0, which is true. So it's like, okay, like it still works. Cool. Yeah, go ahead, draw any hockey stick you want on the graph. As long as it starts at a 1, you're fine. It will work. You can start that one. You can start that one, and you can go all the way down like this. Oh, that is a really large hockey stick, sir. I'm gonna have to. That is not an applicable hockey stick for us today, I'm afraid. I'm gonna have to get rid of that. Even the ones here work, right? Like I can pick up the 6 ones here and then go down to the 6, and that still works. So, you know. Now there's actually another reason for why this is true. So I'm gonna redraw Pascal's triangle here. And you'll be really, and I feel like you'll be mad at me once I show you this one, because like, why didn't you show this earlier? Well, it's because that's not fun. I'd rather you guys do a whole question about candies and suffer than know the fun way to do it. All right, this is the fun reason why the hockey stick theorem works. Okay, so let's draw a hockey stick. This one. Okay. So what we want to do is we want to add this value, and this value, and this value up, right? And we want to make sure it equals 20. Now notice that the one below will always be 1, right? Because it's like the diagonal of ones. As long as you go down to the right, it'll still be a 1, okay? And because of that, now we know that 3 plus 1 here is equal to 4. So we're just gonna do that. And now the 6 plus 4 is also equal to 10. So we just go down. We just go down the list. And you can imagine that if this hockey stick was longer, you could like continue this trend of going down until you hit the little like turning point of the hockey stick, to which you just reach the end of the hockey stick. So that's the Pascal's triangle reason for why this works, because this one drops down here, and then they do this combination with each other like that, and it just works out. Yeah, that makes sense, right? Does that make sense, people? Cool. Okay, so that is the hockey stick identity. So let's do some practice together very quickly to see if we know how to apply the hockey stick theorem, right? So this should be pretty quick. If you memorize the hockey stick theorem. So my first question is, what is 3 choose 3 always summed up to 11 choose 3 like this? So what is this value? Who would like to let me know? Well, what is this value equal to in terms of, given hockey stick theorem, what would this value be? In terms of a combination, you don't have to give me like the value yet. Someone let me know what should go in those brackets. Do people know?
Why do some people call parentheses brackets?
Because it's like both. I don't know.
Aren't brackets like the square thing?
They are, but technically the round ones are just round brackets. So you can short form that to brackets.
Okay.
So what goes inside these parentheses brackets? Shapes? I don't know. Well, what should go in here according to the hockey stick theorem? What is this value and this value? Come on, guys. I know you know the hockey stick theorem. We just did it. 76 choose 4. I think you need to calm down there, Charles. Well, I don't know where you get 676 from. You're gonna need to explain where you get 76 from. I agree with the 4. Where is 76 coming from? Did you add all these numbers up? That's what it looks like. No, that's not what it is. Oh, did you? Oh, okay. Damn, so that would be a big number. That is quite a big number. Well, it's 12 choose 4. And again, remember, it's always just gonna be the biggest one plus 1 and the denominator, the lower one plus 1. So it's like n plus. That's why we like to represent it using the m plus 1 r plus 1 form, because it's a lot easier to more digest because it's just the biggest one here plus 1 and this r term plus 1. So that should help you remember if you forget. 12 choose 4, which is yeah, whatever, 495. No one cares about what the value is. Cool. How about 8 choose 4 plus 9 choose 4 all the way to 15 choose 4. Now I know you can't directly apply a hockey stick here, and why? Something is wrong with this hockey stick, and what is it? The 4. Oh, you mean the denominator? Yeah. But it's not like remember a hockey stick needs to start from the ends, right? Which means this needs to be like if we want this to be a real hockey stick, this needs to start from 4 choose 4, which it doesn't, right? However, what we could do is we can just add them in, right? So 4 choose 4, right? These are the terms we're missing. We're just gonna add them in real quick, and we're gonna subtract them off, right? Because you can do that. And I'll try like this. Cool. Okay. So knowing that, what is this portion? What is this portion here? What will that be equal to? That portion, that portion. Yes. What binomial? What combination will that equal to? Again, remember if you forget the thing. Yes, 16 choose 5. Yep, that's right. Right, and again, it's always gonna be if it's a complete hockey stick, it's always gonna be the biggest one plus 1 plus 1. Don't forget. Easy way to not forget. Just add 1 to each one of those. Cool. What about this? What about this part? What about this part? Is there a value that this might take on? Hey, choose 5. That's correct. This is another hockey stick, right? This is n is 7, r is 4. So what that means for us is that we can have partial hockey sticks. The partial hockey sticks, you just have to subtract this portion here, but that portion itself also contributes a hockey stick here, because this itself is a hockey stick. So you just subtract this value here, and that would work. Cool. 16 choose 5 minus 8 choose 5, which I will save you the work because it is a big number. 4,312. All right, does that make sense? Cool. If that makes sense, then let's for the rest of this class, we're going to spend we can obviously do A, B, C here, right? Of 13.5.1. However, did you know that in combinatorics there are many ways to solve problems? Right? We learned that last time. So I also want to see if you guys can do 13.5.2b. Not specifically A, because I don't think the blocking argument makes sense. It's like that doesn't work. So try making a committee forming argument to show the hockey stick theorem is true. I think that's a fair question I could ask. Yeah, that's about it. Cool. Yeah, this is a pretty hard committee for you, but we have time, so I'll let you guys in. 40 minutes, go. Not 40, 20. Why did I say 40 minutes? That's a lie. 20 minutes. Go to 5:46. I'll pause the recording. Okay, so look at your assignments if you have one, and yeah, get ready to talk about it. Starting with 13.5.1a. That was quick. Yep. 13.5.1a. You use the identity. Yes. This is a direct application of the. Oh, you don't have the book with you. That may make it hard for you to do part B. That would make it pretty hard to do part B, I think. Ray and whatnot. All right. So yeah, as Nancy said, sorry to put you on the spot, Ray. Right, this is a direct application of n equals 7 and r equals 2. And this is until you be 7 plus 1, choose 2 plus 1, which is 8, choose 3. Yep. Awesome, and that is 56, FYI. Cool. Part B, Ryan. Ray might not be around. I don't know. He might. Are you there? If he's not, then yeah, like that's fair because like he didn't have a prom initially. That's fine. I guess we can wait for Rand in a bit. I'm just like put this here to notice him in case he sees it. Part C, Rocky. Let's just skip ahead to that part for now.
I'm still typing it up.
All right, yeah, take your time. It's good.
I'm back. Why is my name on the? Oh wait, am I supposed to do that one?
Yes. We had Aaron he's in the car, so he doesn't have the book with him, so it makes it pretty hard for him to do problems. So yeah, so I put your name there because you didn't seem to be responding, so I was like, okay, maybe he's like away from the keyboard. Yeah, but you've been assigned to part B.
I got 325.
325. And how did you get 325, my good sir?
Yeah, I got 325 by basically just adding 5 choose 3 all the way to 10 choose 3. And then and then basically just calculate it.
Oh, like you did it like you made like number by number, like you actually.
No, I didn't do that. I'm just like saying, just like calculate it as generalized.
Oh, so you like okay, so but yeah, so you like skipped ahead. You just like use the quote unquote general formula. Okay, that works. But yeah, I mean, it's not really a formula. I mean, I guess it is. You could say it's an identity. Which stems from the fact that it's not a complete hockey stick, so you like complete it. Doing so will get you that the left hand portion here should be equal to 11 choose 4, and the 3 choose 3 plus 4 choose 3 should be 5 choose 4, and that gives you 325, as Ryan said. Awesome. And Rocky looks like he's produced a solution as well. Yep. So for this question, this is actually a left facing. This is the reverse hockey stick. Right, it faces the other way. But numerically, it might be hard to identify. So the best way to do this is to change everything. Is to perform n choose r equals n choose n minus r. Right. So it just goes 6 choose 6 minus 0, which is 6. 7 times 7 choose 7 minus 1, which is 6, and they're all 6 in the end. Right. That's the pattern there. And then you can use hockey stick to 16 choose 7, which is actually 11,440, as Rocky says. So good work. Cool. Does that make sense to people? All right. So hockey stick, you can use it in these different ways. That's the idea. And use a count. Yeah, that's fine. For 16 choose 7, that's fine. I don't actually expect you to actually do that by your hand. But I know some people did, so whatever. Now you can use calculator for like big ones. For small ones, I expect you to know how to do it at least. But if you use a calculator to actually compute the value of a common, like a choose notation, that's actually fine. Finally, I'll quickly go over how you can, unless someone came up with something. Did someone end up coming with a committee forming argument as to why the hockey stick theorem works? It's not easy. This is like not because like there's so many additions and stuff. So I totally understand if you didn't get it. Does anyone know? Or no? I mean, I just want to see if someone has a solution. I'd rather, it'd be cool if I heard their solution. No? Anyone else? I'll give you guys like 10 seconds to respond. Going once, going twice, going for 3 seconds. It's not how you actually do auctions. Going for 5 seconds, 6 seconds, 7 seconds. Yeah, okay, I'm just gonna assume now. Awesome, so I'll do it. So we want to show the hockey stick theorem is true, which of course I will write over here. R plus plus 1 choose R plus N choose R is equal to N plus 1 choose R plus 1. So hopefully, right? So first of all, let's consider we have N plus 1 people, and we want to make a committee of R plus 1 committee, right? So of course that will give us N plus 1 choose R plus 1 ways, right? That's what it is. Now, what if we gave now in the past we've treated these people as equal, but what if we gave everyone a rank? Specifically, let's say we have rank, let's say we rank them from 1 to N plus 1, okay? Where N plus 1 is the highest rank, right? This is the top person. This is the less top person, okay? Right, so basically now we're assuming that each of these people, they're actually different, right? And they actually have a different rank in the club or whatever this is. So you want to form a committee. So now let's consider this. And now let's say within the committee there's a president, okay? And the president of the committee will simply be the highest rank in the committee, okay? Highest rank in committee. Now this is a very weird committee because you could technically have the bottom R plus 1 people and like completely ignore all the top folk and then be like, haha, the R plus 1 person is the president. All right, so let's assume there's a president position, okay? The highest rank in the position. What we do now is we case on the number of committees we can form depending on who the president is, right? So first of all, notice that we have to make an R plus 1 committee. Then the rank of president has to be at least R plus 1, right? Because it can't be anything less than R plus 1 because that would imply that there's less than R plus 1 people in the committee. So we know that the rank of the president has to be at least R plus 1, right? Does that make sense? Do people see why this is true? Right. Okay, I'll take the silence to mean yes. So if we know the rank of the president is at least R plus 1, then we can case on who the president is. For example, let's say president is equal to N plus 1. Like that's the most feasible case, right? If the president is N plus 1, then that means we can form the committee. We can form the remainder of the committee, the R people, based off the other N people, right? So we have N choose R ways to do that. Now let's assume the president is N plus 2. If the president is N plus 2, that implies that N plus 1 is not in the committee, which means in reality, we only have N minus 1 choices of people, and we still have to choose R people from them, right? Because we're basically ignoring the N plus 1 case. And you'll notice hopefully the pattern here, where if, for example, if the, no, that's not plus, what am I doing? No wonder. N minus 1 and not N plus 2, N and N minus 1. You go descending order. If the president rank is N minus 1, then you can only choose from people from 1 to N minus 2. So you have N minus 2 choose R. And you can do this all the way to the number of ways to have R plus 1 as the president, to which there are R choose R ways, right? And then you add these all up and you get the hockey stick theorem. Cool? And this does cover all possible committees, right? Because, with or without the ranks, we have covered all of them. So that should do it. Does that make sense? Yep, we love committee forming arguments. Everyone's favorite. I know it's definitely you guys' favorite. No, you got me. Okay, if that makes sense, then that is all for today's class. Thank you guys for coming. I'll grade your homeworks tomorrow, probably. Yeah, I have time tomorrow. And I will release homework not momentarily, but sometime today. Cool. Awesome. Thank you for coming today.
Bye.
Bye-bye.